Hello everyone. So this video is going to focus on the second part of graphing polynomials. If I were to bring back the first part, we did some vocabulary where we talked about the end behavior, which is a general shape based on our chart. We did factoring of four-term polynomials. We also did factoring with trinomials, and we talked about multiplicities. And in class, I gave you a couple extra practice problems with some answer keys that you could have practiced on your own. Just to review, I'm going to do one problem with you before I move on to what is the newer stuff. So here we have a trinomial, and we're going to be factoring, then solving using the zero product property to find those roots. Then once we have the roots, we're going to sketch a graph using our end behavior and those roots that we have found. So the first thing I want to do here is, I notice it's a 1, 2, 3. It's a trinomial. So I am going to factor pulling out the GCF. So what do these three things have in common? They all have an x to the power of 4. What I am left with is an x squared minus 11x plus 30. Now you can go off to the side here and factor this. So you get 30 and negative 11. You would get negative 6 and negative 5. Two negatives give you a positive. Two negatives add up to a negative. So rewriting this, I would get x minus 6, x minus 5, and bring down my x to the power of 4. So before I move on to the zero product property, I want to talk about this x to the power of 4 real quick. Remember that we are going to have a multiplicity here because of the exponent. When I did that problem in class, depending on what class you were, I gave you some version of this. So if it's an even multiplicity, it's going to have a parabolic shape, meaning it's going to be one of these at that given point. So here we saw that this was a 0, 0 multiplicity 2. So at this point, 0, 0, we had a parabolic shape at that given point. That doesn't mean that the whole shape is a parabola. It means that at that point, we had a parabola. Similarly, with the second one that we did in class, we had degree 4, but we only have 2 roots, each of which had a multiplicity 2. So at each of these points, we had a parabola. Here in blue, I did my 0, 0, so here was a little parabola. At negative 3, since that was also a multiplicity 2, I had another little parabola. Whenever you have an even, you will have a parabolic shape. Whenever you have an odd, you'll have more of a cubic shape, which is more like a little swerve. So if we were to look at our end behavior chart, if you have an even, it'll be one of these. If you had an odd, it would be one of these. And we talked about it, you don't know which direction, positive or negative, until you start graphing, depending on where that root is on your chart is the direction it would go on. So here, automatically, I know that this is going to have a multiplicity because of the exponent. So I'm going to go ahead and zero product property this. So x to the power of 4 is equal to 0. X minus 6 is equal to 0. X minus 5 is equal to 0. X is equal to 0 multiplicity to the exponent, which is 4, meaning that at that shape, at that point, I'm going to have a shape of a parabola. Here I have x is equal to a 6, and here I have x is equal to a 5. So if I were to take those roots over, so I factored here, I solved using my zero product property here. Now I'm going to sketch using my roots. So I have a 0 from here. I have a 1, 2, 3, 4, 5, and 6. Okay, now I'm going to use my end behavior. So I'm looking at this first term right here. I have an even exponent and it's positive. So even positive, my end behavior will look like this. So I like to go just a little bit outside of my roots, like that. Now I am going to follow the multiplicities. Remember that if it's multiplicity 1, like these are, you're going to go straight through. So I'll write that down. Multiplicity 4 tells me I'm going to have a bit of a parabolic shape like this. But these two are both multiplicity 1, meaning they're not repeated. So it's going to go straight through. It's not going to have a bounce back like a little parabolic shape like this. So I'm actually going to start with this one because I know that these 2 points are just going to be straight, and it's those two there. So from here, I'm going to go straight and straight. Now I know that at the 0, I'm going to have a multiplicity 4, so it's going to be a bit of a parabola. So if you notice, I'm trying to connect this and this going through that point, which gives me that parabolic shape that I want. Like that. Now, the bigger the exponent, the flatter your your parabola will be. Same thing goes with the bigger the odd exponent is, the wider like your swerve would be. But that's it, our review for what we have been doing. This is actually also number 15 of your big ideas, so I kind of just sketched it out for you there. Okay, so let's go ahead and move on from what a trinomial was. This that we're looking at here is a 4-term polynomial. Now, when we did 4-term polynomials, we have broken this up into pairs, so 2 binomials, and then we pull out the GCF. So in this first one, we know we can pull out an x squared, and I am left with x minus 10. But when I look at the second one, 19x plus 30. Now, I know that 19 is a prime number, so unless 30 can be divisible by 19, I can't simplify this. This can actually not be solved using the GCF. So this is not factorable. So if it's not factorable, how am I supposed to solve this? This is where the rational root theorem comes into play. So the rational root theorem says that if f of x, so any polynomial, has integer coefficients, that means that the numbers in front of the variables are all whole numbers, it's not fractions, then every rational solution, meaning this isn't like the square root of 2 or an imaginary number, where it's a factor, has the following form. P over Q, where P is equal to all of the factors of the constant term. So my constant term in this case would be 30. My constant, remember, it's the one that doesn't have a variable. If we think back to when we were naming these polynomials, a constant had a variable to the degree of 0, meaning it wasn't really there. So it's always the one that doesn't have a variable. And Q is the factors of our leading coefficient. And that one's easy to find if we have our equation written in standard form. It's that very first term. So the first thing I want to start off with in this problem is I want to list all of the factors of P and all of the factors of Q so that I can then bring up my fraction. So let's start off with Q, the factors of my leading coefficient. I like to start with Q because it's the first one. I can just find it here. Which in this case, since I don't have a number, I know it's going to be a 1, and it's going to be a positive 1 at that. So what times what gives me 1? Well, that's easy. 1 times 1, therefore my Q is just going to be 1. If you're lucky, that's going to be the case most of the time. Our issues or longer process is going to be with our P. So our P's are constant. I said it was this 30 here. So if I list out all of the things that equal 30, so 1 and 30, 2 and 15, 3 and 10, 4, 5 and 6, and then we said 3 and 10, 2 and 15, and 30 and 1. I just did it this way so I can do from smallest to biggest. Okay, so I know that 1 times 30 gives me 30, but also if I did -1 times -30, I would get +30. If I did -2 and -15, I would get +30. If I did -3 and -10, I would get +30. So for each one of these, I have to bring in a plus and minus. And this is where it gets really long. Because now when I list out all of my possible factors, I have to do each individual p over all of my q's, which, I mean, it's just 1, so we just have to do all of these. So following my rational root theorem, I'm going to do p over q is plus or minus 1 over 1, which I'm not going to put there because the denominator of 1 is just going to give me the same thing. Plus or minus 2, plus or minus 3, plus or minus 5, plus or minus 6, plus or minus 10, plus or minus 15, and plus or minus 30. That tells me that I have 1, 2, 3, 4, 5, 6, 7, 8, 16 possible factors to this trinomial here. To this cubic here. So how would I know which ones are and which ones aren't? That just turns into a guessing game. You can pick either any of the 16 that we have and test it. So that's what we're going to do. We're just going to pick a random one and we're going to try it out. I wish I could tell you there was a shorter way of doing this, but there really isn't. So might as well use the shortcuts that we've already learned to try to minimize as much work here. I'm going to take this 1 and, I can do any of the points, but I'm going to start with 1. And I'll try the positive one first. So to know if it's a factor, I'm going to use synthetic division and check for the remainder. So I'm going to say, and I'm going to keep my sign just so I don't forget since I have a positive and a negative for each number. Bring down my coefficients, 1, -10, positive 19, and positive 30. Positive 1, -9, -9, positive 10, positive 10, positive 40. So here we see that this positive 40 does not equal 0. Therefore, and this is just a shorthand for therefore, positive 1 is not a factor. So that eliminates 1. We still have 15 other to try. So I am going to try, I tried the positive one, I'm going to try the negative one now and see how that works out for me. I feel like right at this point, you've got to be thinking, why is this so long? And it's important to realize that the difference between something being hard and something being tedious. This is something that is tedious, but something like synthetic division isn't difficult. You just have to do it a whole bunch of times. So again, bring down the 1. That gives me a -1 here, -11, positive 11, that gives me a positive 30, multiply -30, get a 0. And you see we got lucky here. 0 is equal to 0, therefore -1 is a factor. And a smiley face, because that only took me twice. So now I can rewrite this equation up here using what I got. So since I know that -1 is a factor, I'm going to turn that into my binomial. So if I were to divide and I'm using this -1, that means that my factor would actually be, and I'm going to rewrite the whole thing here. So here's my original. And I can simplify that. So if -1 is my factor, as a binomial, that would look like this. So remember, we take the opposite. So here, if I were to take the opposite to use synthetic division, I would get that -1. And that's really important for you to keep in mind. Then I bring down what's left over. So remember that I would drop one of the exponents that I started off with. So this would be an x squared, x, and that. So I have x squared minus 11x plus 30. Okay, but I want to keep factoring it. So here you have a choice. You could either do the rational root theorem with this trinomial here and try to find the roots, or you can pick another one and continue doing it and keep testing points. Or what I will do is I'm going to try to factor this the old-fashioned way. Because this is a 2, this is a quadratic. Since it's a quadratic, I can use my x method. Remember that you could only do it when you have that quadratic. So I'm going to do ABC. So a times c is 30, -11. And this is looking a little bit familiar from what we just did. And then I get -6, -5. If you don't remember, we actually had that same trinomial right here. So this is what I'm saying, it looks familiar from this. Now I'm going to rewrite this as x minus 6, x minus 5, and I'm going to make sure I bring down my x plus 1. Here, I'm going to set this equal to 0 to use my zero product property. X is equal to -1, x is equal to 6, x is equal to 5. I'm going to, so now that I have factored it, used my zero product property, I'm now going to use my roots and my end behavior to graph this. So let me draw my graph. I want to know the end behavior, so I'm going to need this term right here. So according to my graph, my chart here, this is a positive and an odd. So positive, odd, I'm going to look at this one here with those end behaviors, and I know my points. So let me go ahead and graph my points. I have a -1. I have a 3, 4, 5, and a 6. And my end behavior is going to be down and up. Each one of these has a multiplicity of 1, meaning it's going to go straight through at each point. I'm going to go up, down, and up. And that gives me my chart. So let me zoom out so I can go over the whole thing again. I know this looks like we did a whole page of for this one problem, but actually it's just from here on down. Still a lot. I'm not saying it's not, but it's just this. It's not the whole thing. We talked about the rational root theorem here, which says that all of our possible coefficients are going to give us our all our coefficients are going to help us give us our possible rational roots to the polynomial of f of x. So we're going to take our p, which is all of the factors of my constant term. What times what gives me that constant? So in this example, we had 30. We had 1 times 30, 2 times 15, 3 times 10, 5 times 6. And then the negatives of those. You will always have the plus and the minus. Our q is the factors of our leading coefficient. So since in this case it was 1, we just had 1. If you had, for example, 4, then you would have 1 times 4 and then 2 times 2. So then you would actually have 1, 2, and 4. If that was the case, if you had a 4 here. In this case, we didn't. And then you need to set it in this form. So we did all of the p's over all of the q's, and we got this. You would have gotten fractions if this was a different number. So for example, again, if that was a 4, you would have had to do it for every single one. You would have done 1 over the 1, 1 over the 2, and 1 over the 4. So it gets really crazy really fast. Once you've listed all of your possibilities, you're going to start just picking some random ones and testing them out. So here I first started with a positive 1. And I saw that my remainder was not 0, therefore it is not a factor. I then tried negative 1. I saw that my remainder was 0, therefore it is a factor, and I was happy. I then turned that information into my factored form here. So that negative 1 turned into an x plus 1 because remember, it's the opposite. I dropped one of the exponents that I had from the beginning. So it's actually the same one here, but I dropped one of the exponents, so that turned into an x squared, an x, and then not. And that became this here. Since it was a quadratic, I was able to factor using the x method, which is what I did, and it factored out nicely. And then I used the zero product property to find my roots. Once I had those roots, it turned really easy into what we have been doing. Using the end behavior chart, those roots, I was able to find my graph. Remember that the multiplicities are really important here. Since these are each multiplicity 1, they just go straight through at every single point that we have. All right, so let's look at a new example. The last one we did was fairly easy because our leading coefficient was 1. So what happens when our leading coefficient is not 1? The first thing you want to do is see. Maybe you're lucky. Maybe you can use grouping here. If I were to cover these two, I would find that I would have HUCF of x squared, and then I would get 3x plus 1. But if I do it here, I wouldn't have the same thing, therefore I can't use grouping. You always want to test for it because the rational root theorem is not something you really want to do unless you really have to do it, at least until you're comfortable with it. So here I'm going to start off with finding all of the factors to my q. And remember that my q is the leading coefficient. So my q is the factors of my leading coefficient. So here, since it's in standard form, my leading coefficient is the 3. So what times what gives me 3? I have 1. So plus or minus 1 and plus or minus 3. Now already I know that's going to complicate things because instead of just having a denominator of 1, which gives me the same number, now I have a denominator of 3, which is going to make things a little bit more interesting. For my p, I'm going to have all of the factors of 21. So I have positive negative 1, positive negative 2, positive negative 3, positive negative 4, 5 doesn't work, 6, 8, 12, and 24. So now when I list all of the possible roots, I get all of my p's over all of my q's. So I'm going to start off with a denominator of 1, my q 1. So I get plus or minus 1, 2, 3, 4, 6, 8, 12, and 24. When my denominator is 1, again, I can just list the same thing because any number with a denominator of 1 is just that same number. But now when I look at my 3's, and I'm going to do that in a different color. So in green, I did the 1. In this light green, I'm going to do my denominator of 3, where my q is 3. I have plus or minus, so p over q, 1 over 3 plus or minus 2 over 3 plus or minus 3 over 3 plus or minus 4 over 3, and so on. Oh, right, you can't even see these anymore. Let me zoom out. Okay, fun, right? These are all of the possible ones that can be a factor to this. So many possibilities. I have 1, 2, 3, 4, 5, 6, 9, 10, 11, 12, 13, 14, 15, 16. Each one of them positive or negative, so I have 32 options. But I am going to decrease these a little bit. I notice here that I have a 3 over 3. Well, if I were to simplify that, I get 1, which is already over here. I also have a 6 over 3, which again, if I were to simplify that, gives me the 2. I have a 12 over 3, which simplifies to 4, and then a 24 over 3, which were to simplify to 8. So luckily, some of those are repeated. I can cross out 4, which actually means 8, and I decrease my chances there. Not very helpful, but still, it's better than nothing, I guess. Again, I'm going to pick any random number that I want. I started off with the 1 last time. You can try the 1 if you want to. I'm going to just randomly pick, I don't know. Let's do a positive 3. Just because. There's no order to this. There's no like shortcut or secret. It's just you have to try each one. So that's 3, 9, 10. Hey, look, we got lucky. Since this remainder is equal to 0, honestly, I wanted the first one not to work. I wanted to do it at least twice with you guys, but I ended up getting too lucky. Since the remainder is 0, x plus 3 is a factor. So now I can rewrite this. I'm kind of bummed it worked out so nicely on the first try. So since plus 3 is a factor, that would turn into an x. Remember, it's the opposite, so minus 3. What I would be left with is a 3x squared plus 10x minus 8. And then equals to 0. Since I have a square here, I can try to factor it. But unfortunately, this one would take a little bit longer than what we've been doing. Remember that you could go from the x to factored only when the a is equal to 1. In this case, it's not, it's a 3. So I know already I'm going to have a little bit more work than what we have been doing. I want numbers that multiply to negative 24, but add to that 12 and negative 2. Remember that in your box, you have the first term and the last term. You want to pull out a GCF, bring it over. So here would be a negative 2, here would be a plus 4. So now my factored form would be x minus 3, which I'm bringing down straight from here, and then my two factors from there. Do my zero product property. So x minus 3 is equal to 0, x is equal to 3. X plus 4 is equal to 0, x is equal to negative 4. Now here I have something that isn't as straightforward. I'm going to show my work on it, but it's not very different. You want to get the x by itself, so you get rid of the 2, and doing inverse operations, you get 3x is equal to 0. From there, you divide by 3 on both sides, and you get x is equal to 0. So your roots become 0, negative 4, and 3, each with a multiplicity of 1. All right, so here is my graph. I'm going to go ahead and plot these points. I have a 3, I have a negative 4, and I have a 0. I need to know my end behavior. So taking this first term, I'm going to draw my end behavior chart down here. It's a positive and odd, so positive, odd, I have that one there. My arrow and my arrow. Each one of these has a multiplicity of 1, so it's going to go straight through at each of those points. Like this, and like that. And that becomes my sketch. I'm going from the top again. We want to know all of the possible roots. To do that, we need to find our Q, which is all of the factors of our leading coefficient, which was 3. Our P is all of our factors for our constant, which is the term that doesn't have a variable, which is all of these. Remember, each one has a plus and a minus. When you put them together, though, they balance out, so you just need one plus or minus. You're not dividing like a plus or minus 3 divided by a plus or minus 1. It just stays, you just keep the 1 plus or minus sign. These were all of the possible combinations. So I took each one of these and I used these denominators for each one. So first time around in this dark green, I used that plus 1. Second time around with the light green, I used the same P's, but I changed up the Q, and I got these. I then chose just some random number. I could have chosen positive 8 or negative 24 or positive 1. I ended up getting lucky on the first try, even though I really didn't want to. I tested that plus 1, and I got a remainder of 0, which told me that plus 1 is a factor. These 3 little dots are just short for therefore. You don't need to know what you don't have to use them if you don't want to. Since I knew that x plus 3 was a factor, I turned it into a binomial, taking the opposite. So if this is a plus, then this would be a minus. And I brought over what was left over here, and it turned into my trinomial. Since it was a quadratic, I was able to use my x method. Since my a value was not 1, I had to use the xn box, which gave me my 2 factors here. Use a zero product property for each one. Now, although that, why did I say 0? Oh, this is, wow. This is a 2, and this should be a 2/3, which would make this dot right here. So then it's a little bit off of the 0. Close to the 1. All right, sorry about that. I'm just used to the zeros all the time. So I moved it over. I got 2/3, and that's that point right there. And then my other ones became that. I'm sure most of you guys caught that, hopefully. So 2/3, that your two other points came from here. You used your end behavior from here and your chart, and you continued it to that. All right, so this is what you will have on your big ideas. You have 5 of these to do on your own. They are due on Monday. And then you have 5 other review ones, which we're kind of doing in class. Good luck, and let me know if you have any questions. Toodles.